I mentioned yesterday how this conics chapter or topic is an extension of what we looked at last year with parametrics and the parabola. So let's have a look at the parametric form of our conics. The circle, not that we really see it that much, but just to complete the set, I guess, of conics, we should look at the circle. We know its standard equation is x squared plus y squared is equal to a squared. The parametrics for it, there's a random point P. If I simply draw up a triangle, the parameter we use for this type of parametrics is the angle that when you join the point up to the center of the circle, the angle it makes at the center. And we can get it in terms of that parameter. And then, of course, the radius being the fixed amount we're also going to use. So using that with that triangle, I can get an x value with a simple trick. So x over a would be the cosine of theta. So x is a cos theta. And then y, well, that will become a sine theta. So they are the parametrics for the circle. So the parameter is theta. So a little bit different to the parabola that we saw. You remember the parameter was t. That just represented your t as you're going around the parabola. All right. We can prove it very easily, if you don't believe me that that just worked. All I got to do is substitute it in, and you'll notice we just get our familiar cos squared plus sine squared, which is 1. So indeed, x squared plus y squared does in fact equal the radius, in this case, a squared. Okay, well, let's have a look at the ellipse then. It also has to do with the angle made at the center, but we've got to look at it very closely. P is there, some random point on my ellipse. I draw in that auxiliary circle that I talked about yesterday. Well, and whilst it's useful for drawing the ellipse, probably its main use is for this, describing the parameters. So that's our auxiliary circle, x squared plus y squared equals the major semi-axis squared, so a squared in this case. So theta is not the angle when you join P to the center. Right? That's a commonly held misbelief, mistake, call it what you like. Theta, the parameter, actually refers to if you draw a vertical up to the auxiliary circle and then you join that point up to the center. That is the angle we're talking about in our parameter here. So looking at that large blue triangle, I can get an x value, same as I just did with the circle, because now I'm talking about the circle. And surprise, surprise, it turns out to be the same as the circle, a cos theta. But to get the y value, I can't do that. To get the y value, I draw in the smaller circle. X squared plus y squared now equals b squared. Because what happens with the ellipse, if I draw a horizontal from that point, it will meet up with the hypotenuse. And so the angle at the center is the same for both triangles. And that's why we use that angle, because it's the same for both the auxiliary circle and the smaller circle as well. And so to work out the y value, I'll now use this smaller triangle, and I get y over b is equal to sine theta, and so we get y equals b sine theta. And so there's our parametrics. Very similar to the circle. It's just that the coefficients in x and y are different because we're talking about an ellipse rather than a circle. And again, I can easily substitute those in to show that they do indeed work. X squared on a squared plus y squared on b squared. You see the a squareds cancel, the b squareds cancel. Once again, I get our familiar cos squared plus sine squared, which is equal to 1. All right. Equations of tangents and normals. You remember with our parametric questions, we had key lines that we were always finding. Chords were other ones. Points of intersection, things like that. So let's find the equation of the tangent and the normal. So there's our equation. Obviously, I'm going to need to find the derivative if I want to find the slope of the tangent. But I've done it implicitly rather than trying to make y the subject of this whole thing. Implicitly is a lot quicker. So I get 2x on a squared plus 2y on b squared. But of course, I've differentiated that with respect to y, so I've got to multiply it by dy dx. And differentiate 1, we get 0. Rearranging that, oh yes. So of course, remember, implicit differentiation comes from our chain rule, rates of change, call it whatever you will, but that idea. Dy dx then In this case, we're going to need to substitute in both the x and the y value in order to work out the slope. So we get minus b squared x on a squared y. Random point x1, y1. So I'm just using Cartesian coordinates to start off with. So obviously the slope becomes minus b squared x1 on a squared y1. All right, so there's our point x1, y1. So the tangent, point slope formula, y minus y1, etc., etc. If I expand out, and I've just rearranged it in a certain way, you'll notice on the left-hand side, I have everything that involves the pronumeral x and y. Remember, x1 and y1 is our point there, so they're actually numbers, they're not the pronumerals. And then on the right-hand side, I've put all the numbers that are by themselves. So b squared x1 squared plus a squared y1 squared. Dividing everything by a squared b squared, and something very nice happens. On the right-hand side now, you'll see I've got x1 squared on a squared plus y1 squared on b squared. Well, that's very familiar. That's the equation of the ellipse. And x1, y1 lies on the ellipse. So therefore, I actually know the value of the right-hand side. It's got to equal 1. Because when I substitute x1, y1 into the equation of the ellipse, I must get 1, because that's what the formula was. Have a look at the equation of the tangent. It's very, very similar to the equation of the ellipse itself. Remember the ellipse, x squared on a squared plus y squared on b squared is equal to 1. Have a look at what we've got. x1 times x. If I was to sort of rub out that 1 there, you'd have, oh, x times x squared. And y1y on b squared. Again, if I was to rub out that 1, pretend it wasn't there, I'd have y times y squared. So the actual form of the tangent, what it looks like, is very similar to the equation of the ellipse itself when we're using Cartesian coordinates. So x1x on a squared plus y1y on b squared is equal to 1. All right, let's do our normal. So slope of the normal will be the negative inverse. So we've got a squared y1 on b squared x1. Expanding that one out, and again, I've moved everything that has a pronumeral, so the x and the y on the left-hand side, everything that just has constants on the right-hand side. I'd love it if there was a nice, neat trick like this last one, but there's not. I'm just going to divide everything by x1, y1, and that's really the best I can do. So a squared minus b squared. I suppose it could link with the eccentricity. Remember we said eccentricity squared was a squared minus b squared over a squared? Now you're going to have to derive these each time anyway. So as I was saying, the other way I could write it would be a squared e squared. Okay. Well, what about if we use our parametric coordinates rather than our Cartesian coordinates? So now I'm calling P the point a cos theta, b sine theta. So the derivative will now become, subbing in the x and the y value, I end up with minus b cos theta on a sine theta. Do not change that to cotan theta. It's very tempting. You see the cos on sine, you think, oh, that's cotan. Leave it as cos on sine. All right, tangent. Point slope formula. And this is why we leave it that way, because now I'll get rid of the fraction and it will create a sine squared on the left-hand side. And when I expand out on the right-hand side, I'll get a cos squared. And so there's our sine squareds and cos squareds that we like playing with. Same idea, anything that has an x and y I've left on the left-hand side, everything else on the right-hand side. But have a look at the right-hand side. There's ab sine squared plus ab cos squared. So that's just ab. Or I could divide by the ab and leave it with sine squared plus cos squared, whichever. Sine squared plus cos squared is 1. And there is x cos theta on a plus y sine theta on b is equal to 1. The normal, what does that look like in parametrics? So, negative inverse. Now I've got a sine theta on b cos theta. Expand that one out. Again, there's not a nice neat trig identity, is there? We've got ax sine theta minus b1 cos theta. There's that a squared minus b squared again. but now it's times a sine theta cos theta. I'm going to divide everything by sine theta cos theta. And so that's a little bit neater, I suppose, just having the a squared minus b squared plus. It leaves it in a similar sort of format as when I did it with Cartesians, having it equal to a squared minus b squared. Or alternatively, you could say a squared e squared. All right, so to summarise all that, there's our standard ellipse. If I'm using Cartesian coordinates, there's the equation of the tangent. Looks very similar to the ellipse itself. There's our normal, equals a squared minus b squared, or you could write it as a squared e squared. The difference between the two, I suppose, what should we be looking at? Things like this. The normal, the x1 and the y1's on the bottom, and the a squareds and the b squareds are on the top. The tangent, it's the other way round. That's all to do, of course, with the slope being the negative inverse. So you're expecting that sort of thing. Parametrics, there's our tangent and our normal. Feel free to memorise those if you wish, but as I say, you're going to be expected to derive them. And the actual derivation of them really is 2-unit stuff, because it's just, hey, I need the derivative to find the slope, put it into the point slope formula, bang, there's my answer. It's just that we don't necessarily use numbers here. Sometimes the coordinates are pieces of algebra, so a cos theta, b sin theta, making it a little bit trickier, I suppose. Let's do this one. There's my ellipse. X squared on 16 plus y squared is 1. We're going to find the tangent at the point 2, negative root 3 on 2. So say it's X standard, find the equation of a tangent question, really. Yes, I use implicit differentiation to find the derivative, so that makes it a little bit different. I end up with minus x on 16y. Subbing in my point, I get a slope of 1 on 4 root 3. Point slope formula. Let's get rid of those fractions and make it look like a general equation there. So x minus 4 root 3y minus 8 equals 0. Bang, there it is. That, I guess, is the simplest type of tangent question you could get, where they simply just say, hey, find the equation of the tangent. And they've actually given us numbers. Let's do this one. It's in parametric form. So they're telling us the parameters of our ellipse is 2 cos theta and sine theta. And we're going to do it at the point where theta is pi on 6. Now, just a quick reminder, because I'm going to have to differentiate some trig here to do this. Differentiate sine, remember, we get cosine. Differentiate cosine, we get negative sine. All right. You've got two choices. You could go back and recreate the actual equation of the ellipse itself. So if x is 2 cos theta and y is sine theta, what would that be? X squared on 4 plus y squared is equal to 1. Okay, so you could recreate that. But it's a lot quicker to just use our parameters. X equals 2 cos theta, so dx to theta is minus 2 sine theta. Y is sine theta, so dy to theta is cos theta. So dy dx is dy to theta times the theta dx, and there's our derivative, cos theta on minus 2 sine theta. Okay. At the point where theta is pi on 6, that slope becomes minus root 3 on 2. Point slope formula. Hang on, where's my x value and y value? Well, all I know is it's the point where theta is pi on 6. So again, I go back to the parameters. Well, the x value then is 2 times the cosine of pi on 6. And the y value is the sine of pi on 6. Play around with that. Make it look like a general formula. 4x minus 2 root 3y minus 3 root 3 is 0. If y equals mx plus k is a tangent to the ellipse, x squared on a squared plus y squared on b squared is 1, then a squared m squared plus b squared is equal to k squared. That's what we're going to show. Okay, y equals mx plus k. Something to do with the tangent, so x is a cos theta, dx to theta, minus a sine theta. Basically, I'm doing exactly the same thing. I'm finding the slope of the tangent here. Y is b sine theta, dy to theta, b cos theta. All right, I know the derivative is minus b cos theta on a sine theta. Now, if y equals mx plus k is a tangent, then I know the derivative must equal m. because there's the equation they've told me, y equals mx, slope of the tangent is m, the derivative also measures the slope of the tangent. So m is minus b cos theta on a sine theta. Playing around with that, I come up with an equation. am sine theta plus b cos theta is equal to 0. All right, that's one equation. The other thing I know is that the tangent meets the ellipse at our point, our parameter that we pulled out, a cos theta, b sine theta. So therefore, it must also satisfy the equation of the line. So b sine theta is am cos theta plus k. Rearrange that one. I now have some simultaneous equations. Okay. I'm going to square the first equation, as you do. A squared m squared sine squared, twice the product, so 2ab m sine theta cos theta, and then b squared cos squared. I'm also going to square the second one. And you'll notice the middle term, the twice the product, will cancel when I add these together. But not only that, I also end up with all these sine squareds plus cos squareds, which is of course 1. am squared plus b squared is equal to k squared.